Segmentation fault, core dumped. Your program just died, and that's the entire message. You Google it, you find a forum post that says you're accessing memory you don't own, and you close the tab, because that sentence doesn't actually mean anything to you yet. That's not your fault. Nobody sat you down and explained what memory you own even means, because that idea lives one full layer underneath the language you write in. It lives in the operating system. By the end of this video, you're going to understand exactly what happens in that layer. The one running underneath every program you've ever written, whether you've thought about it or not. Why a process can't see another process's memory, but two threads inside the same process can step all over each other's. Why your code has to ask permission just to read a file from disk. How your laptop runs 200 processes at once on 8 CPU cores without any of them noticing. And exactly what a segmentation fault actually is, the moment it happens. A process is a sealed apartment. It gets its own private address space, its own memory, completely walled off from every other process on the machine, plus a record the operating system keeps on it called a process control block. Exactly what that process needs to resume later, its registers, its program counter, everything. One process genuinely cannot reach into another process's memory. That wall is enforced by the hardware itself, not just a polite convention. A thread is a roommate inside that same apartment. Every thread inside a process shares the process's memory completely, the same heap, the same global variables. But each thread gets its own stack and runs its own independent sequence of instructions. That's exactly why threads are fast to create and fast to communicate through, and exactly why two threads modifying the same variable at the same time is a real common bug called a race condition. They're not protected from each other the way two separate processes are, because they're living in the same room. Picture two threads both incrementing the same counter starting at 0. Each one reads the value, adds 1, writes it back. If both threads read 0 before either one writes, they both write back 1, and a counter that should read 2 after 2 increments is stuck at 1. Neither thread did anything wrong on its own. They just weren't protected from stepping on each other, because nothing about sharing a process's memory ever promised they would be. And each thread, even while sharing that room, still keeps one thing private, its own stack, the region of memory holding its local variables and the trail of function calls it's currently inside. That's also where Stack Overflow comes from, and it's a more literal name than most people realize. Every thread stack has a fixed size, decided when the thread starts. Recurse too deep, and you're not being punished for bad style. You're a thread trying to grow its private room past the wall the operating system built around it, and getting the same kind of hard rejection a process gets for reaching outside its own memory entirely. Every process believes it owns the entire address space of the machine, from 0 all the way up to the maximum a 64-bit address can reach. That belief is a lie, deliberately maintained by the operating system, and it's called virtual memory. The real physical RAM in your machine is chopped into small fixed-size chunks called page frames, and a piece of hardware called the memory management unit translates every single address your program touches from that fake, private, virtual address into a real physical one, using a lookup structure called a page table. This is exactly what a segmentation fault is. It's not vague at all, it's the memory management unit looking up an address your program just asked for, finding no valid mapping for it in the page table, and refusing the request. You reached for a room that was never assigned to you, or one you already gave back, and the hardware said no. And this same system is why running out of memory doesn't instantly crash everything. Pages get loaded on demand, only when actually touched, and the operating system can quietly swap pages you're not using out to disk to make room for ones you are. This is also why the jump from a 32-bit to a 64-bit operating system was such a big deal, and it has nothing to do with speed. A 32-bit address can only count up to about 4 billion distinct locations, so a 32-bit process is hard-capped at roughly 4 gigabytes of virtual address space total, no matter how much physical RAM the machine actually has. A 64-bit address can count into the billions of billions. The cap effectively disappears. The virtual address space got bigger. That's the entire announcement. What's inside a given address was always a separate question, answered by whatever the page table happens to be pointing at right now. Think of it as two different ID badges. Your program runs holding a user mode badge. It can only open the doors inside its own sealed apartment. The operating system's kernel holds the other badge, kernel mode, which opens literally every door in the building. The disk, the network card, every other process's memory, the hardware itself. Your code is never handed that second badge directly. Ever. So when your program needs something outside its own walls, read a file, open a network connection, allocate more memory, it can't just reach out and grab it. It rings a doorbell. That doorbell is called a system call, and it hands control over to kernel mode code, which fetches whatever was requested on your behalf and hands the result back. That handoff, called a trap, is exactly why system calls are measurably slower than a normal function call in your own code. You're not just running a function, you're switching the entire privilege level of the CPU and switching it back. Something as ordinary as reading a file read, in most languages eventually calls the exact same underlying system call. Isn't your program pulling bytes off a disk directly? Your program can't touch the disk at all. It rings the doorbell, the kernel mode code talks to the actual disk driver, copies the bytes into a buffer your process is allowed to see, and only then hands control back. Starting a whole new program works the exact same way, just with a bigger request behind the same doorbell. On a Unix family system, that's actually two separate system calls doing two separate jobs. One clones the calling process into a near-identical copy, and a second one replaces that copy's memory with a completely different program, loaded fresh off disk. Every terminal command you've ever run, every child process any language runtime has ever spawned on your behalf, goes through that same two-step handoff into the kernel. Never a program directly conjuring another program into existence on its own. Your laptop has, at most, somewhere around 8 to 16 CPU cores. It is very likely running 200 processes or more right now. The operating system scheduler is the reason that isn't a contradiction. It hands each process a tiny slice of time on a core, on the order of a few milliseconds, then swaps it out for the next one in line. It happens so fast that from the outside, everything looks simultaneous, even though at any single instant, each core is still only ever doing exactly one thing. The swap itself is called a context switch, and here's the part that makes it possible at all. Before a process gets pulled off a core, the operating system writes down its exact state, every register, the program counter, the stack pointer, into that process control block from Chapter 1. Later, when that process gets its next turn, the operating system loads all of that back in, and the process picks up mid-instruction as if it never left. Interrupts force this too, a timer tick saying your slice is up, or a disk saying the data you asked for is ready. Both yank the CPU's attention away immediately. This is also the piece that explains a program that looks completely frozen without having crashed at all. A process isn't just running or not running. The scheduler tracks it moving between distinct states. It's ready, meaning it wants a core and is waiting in line for one. It's running, meaning it currently has one. Or it's blocked, meaning it asked for something through a system call, a file, a network response, a lock held by another thread, and it physically cannot continue until that answer comes back. So the scheduler pulls it off the core entirely and hands that core to someone who can actually make progress. Your program isn't broken in that state. It's parked on purpose, until the one thing it's waiting on shows up. Here's the part that explains why more tabs, more containers, more background processes doesn't just use more memory. It makes literally everything slower, even the things that were already running fine. None of this illusion is free. Every context switch's real overhead, the CPU's fast-on chip caches and its address translation cache both get partially invalidated every time, so the next process has to warm back up before it's running at full speed again. Pile on enough processes competing for too few cores, and the operating system can spend more total time switching between work than actually doing it, a real measurable state called thrashing. Virtual memory has its own version of the same trap. If your machine's physical RAM genuinely fills up, the operating system starts swapping pages out to disk to make room, and disk, even a fast SSD, is dramatically slower than RAM. If your programs keep touching pages that just got swapped out, the operating system ends up constantly shuffling data back and forth to disk instead of running your code at all. That's the exact moment your fan spins up, your cursor freezes, and everything on the machine grinds to a halt at once. Not a bug in any one app, but the underlying memory system losing the argument against physics. It's also why closing one memory-hungry tab can instantly unfreeze everything else on the machine, including programs that had nothing to do with the tab you closed. They were never broken, they were just waiting in the same line. So the next time something in your program is acting wrong at the systems level, you ask 3 questions, and each one points at a completely different layer of everything you just learned. 1. Did it crash outright, reaching for memory? That's virtual memory, almost certainly a segmentation fault. Check what address it was actually touching and whether that address was ever really yours. 2. Is it just sitting there, not crashed, not progressing, technically alive? That's a process parked in the blocked state. Check exactly which system call it's hanging on, because something it asked the kernel for hasn't come back yet. 3. Is nothing crashing and nothing obviously stuck, but everything is measurably slower than it should be? that scheduling or paging under real pressure. Check what else on the machine is competing for the same handful of cores or the same finite RAM. 3 questions, 3 layers, and now 3 names instead of 3 flavors of "it's just broken." That segmentation fault from the very first line of this video isn't a mystery anymore. It's the memory management unit doing exactly its job, refusing a request for memory that was never yours. Every single piece of this, the wall around a process, the badge your code never gets handed, the scheduler quietly parking anything that isn't ready to run, was already there, running underneath every program you've ever written, whether you'd given it a name or not. That's really what separates knowing how to write code from understanding the machine that actually runs it. Not more syntax, just finally seeing the floor everything else has been standing on the whole time. And this exact trick, one process genuinely unable to see another process's memory, walled off by the operating system itself, turns out to be the same trick a container uses to convince your code it has an entire machine to itself, packaged up one layer higher so you never have to build the wall by hand. A container isn't a smaller, lighter virtual machine underneath the marketing. It's an ordinary process, wearing the exact isolation you learned about in Chapter 1, with a kernel simply hiding every other process on the box from its view. No new hardware trick, no new physics, just the same wall, drawn in a different place. None of the 5 mechanisms in this video are exotic. They're not the kind of thing you'll only need once a year on a hard problem. They're running right now, underneath the tab this video is playing in, underneath your editor, underneath literally everything on the machine in front of you. Go watch Docker Explained on this channel to see precisely how far that same illusion goes once it's built one layer higher than the operating system itself.